Dear friends, we will start, as promised, the celebration of geometry, Euclidean and not so Euclidean. The celebration of geometry will have several parts. Of course, there will be discussions on the boards, but what a better way is to start doing some readings from a book which celebrates Euclid's elements. And I have shown you the book earlier in one of the programs, I don't remember exactly, called Encounters with Euclid by Benjamin Wardhaugh. And this book tells you what happens to that book, how it is that it maintained in print, and people are still reading it after so many, almost 2,300 years. And so, what happened to that? More than 2,300 years. So, what happened to that book? How did it gain so much popularity, and what is the history of it still been there? And the knowledge that Euclid's elements give out, or rather it imparts on many people. We will also have a discussion about certain bonus books about geometry, which will also come under our celebration. But let us do one thing. Today's program would be called Readings in Geometry. So it is the start of the thing. So this book will be a part of the Readings in Geometry, and we will read several books, several chapters of this, not fully, partly, the interesting facts. And the story also comes down to India and to Calcutta in College Street. So there is a lot of fun in this book. It's actually not very costly. Uh, it is 5.99. In Amazon, it will be lesser. But it's a very, very good book, very beautiful, huge, I would say, entertainment. And so, let's start our program. Let's begin with Euclid. And thank you, subscribers. I'm delighted. I become a YouTuber for a moment and say that thanks for making my YouTube channel 10 having 10,000 plus subscribers. Wonderful news, and I thank all of you. As I said, I'll never put a join button there, where my aim is not to ask money from students. So maybe advertisement, it seems that monetary thing is meter is going up. They pay by $100. Maybe I'll show you how much I've got. Maybe just to explore this whole thing with you. Just let me show you. It'll be pretty fun. So here is kind of my, just a moment. Just a moment. I guess I had put it on the airplane mode because I wanted to. So now, let me get out of the airplane mode and let me show you. So here is my YouTube studio, and here is my earning. So you can see through the advertisements I won US dollars 41.90. I don't know how much it will be in, maybe around 3,000 something Indian rupees, but okay, it's through advertisements. And thanks for all of you for watching my video. So I become a YouTuber for some time. So again, let me go back and become a teacher. So this public engagement is a very important thing that I think I would be doing in the future, apart from doing my research. Of course, you can say, oh, you're an old guy now, you can't do much of research. Yeah, as Hardy had said that old men should write books and young men should prove theorems. But I do try to prove theorems a bit. So let me start reading the first chapter of this book. It's called Alexandria, named a town in Egypt, a city in Egypt, ancient city in Egypt, a very flourishing city in Egypt named after Alexander the Great. It's called the Geometer and the King. Alexandria around 300 BC. A dinner, say, a symposium, in a place, in the palace quarter, perhaps in the museum. Museum was essentially the university, they called it museum. Ptolemy was the king in attendance, general, hero, king, and deity. And the talk touches on geometry. Why so hard? He asks. Why is there no easier way? The geometer, a dusty man, but Pot answers, Majesty, there is no royal road to geometry. This is a story which is very much linked to Euclid. Nobody knows whether there is no real record that whether Euclid has really said it. But this is comes like a folklore. Maybe somebody made up the story just like Newton's apple. And it just goes on, goes on, goes on, goes on. Ptolemy snubbed is one of the irresistible stories. The man had been a childhood friend of Alexander the Great, one of his bodyguards actually. Maybe his illegitimate half brother, who knows? He was a trusted general, level headed but capable of grand gesture. He was one of the great survivors too. In the 20 years of chaos that followed Alexander's death, when many abler men died, Ptolemy played and won. And all the successors who eventually carved up Alexander's brief continent spinning empire, he founded the longest and the stablest country. He chose Egypt and he served, never risked it for a larger realm. 14 Ptolemaic rulers followed him until Cleopatra, who is very famous, lost it all in a battle of Actium 250 years later. The first king then of the last Egyptian dynasty, Basileus, to the Greeks, Pharaoh to the Egyptians, inheritor of 3000 years of Egyptian kingship, and yes, a god too. In 306 BC, he defeated an attack on Rhodes so soundly that the altars were erected to him and he acquired the title of savior. By 278 BC, there were Ptolemaic games in his honor, 4 year, just like the Olympics, every 4 years. The geometer, by contrast, a man named Euclid, Eucleides in Greek. A man named Euclid, that's an anglicization, is utterly obscure, historically speaking. Actually, nobody knows who the real Euclid was. Some people doubt whether is there a real Euclid or there's a group of scholars who call themselves Euclid, just like in the modern times, a group of French savants, French scholars, mathematical scholars, call themselves Nicolas Bourbaki, the famous French professor who never existed, but he wrote books. Actually, they wrote those books. Alexander Grothendieck was one of them. The geometer, by contrast, a man named Euclid, is utterly obscure, historically speaking. The story about the royal road is moonshine, sadly. And it is told also about another geometer and another king. And there is little reason to suppose it really happened. There is no reason to suppose. Even his dates sometimes around 300 BC are mere surmise of authors writing centuries after him. Unlike the exceptionally well documented Ptolemy, Euclid left no biographical traces whatever. He founded no dynasty, built no palaces. His legacy was solely intellectual, mathematical rather. But what a legacy! The line of his students at Alexandria outlasted his life. The book outlasted his civilization. The book outlasted every civilization. The book essentially outlasted human, forward movement. And it was the basis of human forward movement. What was this city that produced a man and such a book? Alexandria was the right setting for the elements of geometry. It was Ptolemy's great achievement. Alexander himself decreed the city on the site of what had been a village, and like dozen others, it bore his name. He never saw real stone erected, but Ptolemy took it for his capital, moving the Egyptian royal seat from Memphis. It was a Greek polis in a profoundly un-Greek world, a new foundation in a land where cities were 2000 years old. Ptolemy did everything to make it splendid. It had an assembly, a council, its own coinage, and its own laws. There were broad boulevards, colonnades, avenues of trees, and street lamps. In 322 BC, he kidnapped Alexander's corpse and put it on display in the new royal city. Okay. So there's a lot of history been given here. So let us come to the part where let me tell you where people doubt whether there was a real Euclid. So all of the many famous Greek mathematicians during Ptolemy's time ended up working in Egypt, in Alexandria, in the famous library of Alexandria. Was Euclid another part of Ptolemy's collection? Someone bought in to swell the ranks of the museum. It is not certain whether he was a native to Alexandria or an immigrant, although at this early date in the city's life, the latter is much the more likely that he was an immigrant. An immigrant from where? His austere prose gives no hint of an accent, like Archimedes in the next generation, who wrote a Doric dialect of Syracuse. What came to Alexandria in Euclid's person, and perhaps in the person of other mathematicians, it is not clear whether or not he was the only one. So Euclid may be a symbol of a group of mathematicians. Was a well established tradition of Greek geometry. Greeks like to have things to think about. They liked hobbies. Some Greeks raced chariots, some talked about philosophy, some occupied themselves with politics, some perhaps in the late 5th century BC onwards, some did geometry. Draw a line, square a circle, reason out loud as you draw, play to the inevitable audience. From the beginnings, the long lived game of geometrical reasoning took shape in that famous city. The figure of geometer drawing on the sand remains a part of the image of ancient Greek mathematics to this day, raking in the learned dust, as the Roman orator Cierso puts it. He memorably evoked Archimedes as a man of the dust and drawing stick. Though you have tried to have a detailed diagram, though have you ever tried to draw a detailed diagram in dry sand, pieces of clay, wax tablets, or for showing a larger audience, wooden boards seem more probable. The number of Greek mathematicians was never very large, and they had to write their own ideas to preserve what they found about their lines, circles. There weren't enough of them. It seems for a purely oral transmission to stand a chance, because mathematics cannot be just an oral transmission, it will be lost. People will forget things. So a genre was born, a special style of mathematical writing. That style would come to define mathematics in the West for more than 2 millennia, in constraining any poetic meter, and as long lived. This idea, which Euclid put in his elements, of first having some basic definitions of tools, the objects that you will use, then certain relations between the objects which look so obvious that you don't need a proof and you call them axioms. And then from those axioms comes more involved truths which need a proof based on those definitions and those axioms. And those are called propositions in Euclid. They don't call it a theorem, by the way. There's no word theorem, it's propositions. So he proposes a statement and he tries to prove it. So its components were statements of something to be proved. The diagram with its points labeled with letters, and a chain of reasoning from things already known to things newly proved. So, a theorem now is based on the theorems and the axioms and the theorems previously proved. That is the basic formal structure of mathematics which we use till date. It has not gone away. Euclid, one can say, oh, it's just for the Westerners to think about. But no, Euclid gave an idea which was so fundamental, so beautiful of idea of doing mathematics, so logical that it ultimately spread. You cannot stop an idea whose time has come. So it ultimately spread, and it ultimately spread into something so important that it became the fundamental structure of mathematical thinking all over the world, and that exists till now. The chain ended with the proposed intended result, and the proposition was rounded off with a note that this was to be proved. Quod erat demonstrandum. That is, after every proof, it is written QED. It means quod, Quud, and thus the result, and hence the result. Quod erat, erat, demonstrandum, right? In some cases, it was what was to be drawn. For example, if you go to the first book and first proposition of Euclid, it says, just given a line, draw an equilateral triangle whose sides have the lengths of this line, basically, in our modern language. But it was just how to draw an equilateral triangle, and this is how you should draw an equilateral triangle. So if AB is the line given, so you first take A as a center and with AB as the radius draw a circle, and then B as the center, take AB as the radius and draw a circle. They will, from the drawing you see, they intersect exactly at 2 points. So with one of these intersection points attached, it is C, join BC, join AC. And then because AB is the radius here, AC is the radius here, this is equal to this, and AB is equal to AC, and similarly BC is equal to AB is equal to AC. So that's an equilateral triangle. Beautiful, simple proof. But logicians or too much logically minded people had problems with this proof. They said that it is totally picture driven. It's not without the picture. How do you know that every such instance of a line, those triangles will exactly intersect if you draw it like that in exactly 2 points, not more, not less. So it's not possible to demonstrate such a thing by proof, because this is called picture based proof. So that gave rise to new axiomatic system apart from Euclid, and that was due to Hilbert. And we will come to Hilbert's axiomatic system as we will keep on studying the geometry. So there is a lot of Euclid geometry beyond school which is never taught after your school is finished, but I think that's really not the thing. Studying Euclid's elements is an extremely important part of one's mathematical education. If you don't get it in your school system, you don't in reality learning elements, you don't get in your college system or university system, of course. So it is those who want to enjoy mathematics, it becomes their own responsibility to learn it. So some ancient sources that report when Euclid lived also report that there were written collections of geometrical learning in Greeks by perhaps 400 BC, a century before him. They are quite informative about the subjects involved, even some of the specific results and techniques. The written matter itself has not survived, though throwing it all into doubt. There is a strong temptation to make up genealogies of mathematical ideas when real evidence is lacking. So you do not have an evidence who actually did it. You can now tell that some XYZ did it or people much before did it, and so you would have not evidence. But when you write, you talk about historical things in mathematics, you must need evidence. You must say, okay, this is till now, this is what we know. This is from these results come from this work. Okay. There is a strong temptation to make up genealogies for mathematical ideas when real evidence is lacking. So, yes, maybe the study of circle was done by the Pythagoreans, which is quite natural. Likewise, the work on numbers and their properties had also been done by the Pythagoreans because they were so fond of it. Very probably, the work on ratios was done by a geometer called Eudoxus early in the 4th century BC, 400 years before Christ was born. Some work on regular solids originated from another name, Theaetetus, and also we will talk about the work of Thales of Miletus. The claim that there were before Euclid well developed books called Elements of Geometry seems distinctly more doubtful. So people try to claim that, oh, Euclid has somehow taken some older book and tried to make it better or something like that. But there is no such evidence of it. What was Euclid's role then? He took all the easier material known to the Greek geometers to his day and put it all together in a single book. He organized it both on the large scale and the small scale. He added some new matter of his own, though no one can now confidently identify what was new and what was not. For example, something about solid geometry was definitely possibly new. That primes, they are infinite primes, that is possibly new. So, it has a lot elements have a lot about numbers, about ratios, because that is what is needed when you are talking about geometry, similar triangles, right? Certainly added some new matter of his own, though no one can now confidently identify what was new and what was not. Historians continue to argue, and they always will, about how much compilation and how much composition in Euclid's book, how much he took from others and how much he did. His was a work of collection like Ptolemy's. Ptolemy's was the king collecting people. Euclid, the museum artifact, became himself a curator. The elements, a smaller museum. Yet this museum contained a world. It displays the geometrical style of prose in a relentless ritualistic tramp of proposition after proposition, 400 of them, arranged in 13 books or chapters. Every verb was perfect, imperative, and passive. Let a circle have been drawn. And you expect the circle to be drawn. There was some hypnotic about it, something infinitely calm, some kind of a charm in the Euclidean thinking. In fact, the economics Nobel laureate Amartya Sen, Indian economics Nobel laureate, who is of course very old now, in one of his books he wrote, it's a book called The Country of First Boys, about possibly India's education system, or some note or some more essays on India. He wrote that it was very, because of his own interest in mathematics, that he could give away everything that he has earned in his life to be given a chance to visit Euclid's study in private. And that's very thing that Amartya Sen's love for mathematics is shown is that when Nobel Committee, they asked the Nobel laureates to give something for the museum, so that will be a reminder of him that some of the best things that he had loved. So he gave them some, I think, certain book uh, written by Aryabhatta, maybe the old manuscripts, the real manuscript of Aryabhatta, Arya Samhita, I guess, and then his old bicycle. So Euclid is in the mind of very big people. Euclid is in the mind of all mathematicians. In secret, Euclid is their hero, and of mine too. He had been one of my great heroes, though we would never know who he was. There was something hypnotic about it, something infinitely calm. The book began with definition, what was meant by a line, a point, a circle. Line is a breathless slang. The point is something which doesn't have any dimension or any length, breadth, height, anything. But points actually vary however small you want. Line always have a breadth. It doesn't matter how neatly you draw. The more thinly you draw, the more near and nearer you get to that abstract line, to that real abstract line that Euclid had wrote, breathless length. But in reality, when you work, you understand what is a line, what is a point, and so you know that there are relations among them, and you use those relations to build up your results. It continued with the simplest manipulation of lines and shapes in two dimensions. To draw, how to draw different kinds of triangles, how to divide a line or an angle into two. You see this, today we talk about degree of the angle, degree value or radian value, 30-degree angle, 20-degree angle, 60-degree angle, 90-degree angle. They knew about right angles, but they had no sense of angle measurement in terms of kind of radian and all those things, what we do now. So those came much later. And we seem to have uh, we seem to have forgotten that fact. If you read Euclid, that they were arguing things. That is why it's called the synthetic method. When there was no clue of angles, nothing. Nobody knew what angles are. Angles, they knew what angles are. Sorry, I would not say. Please pardon me. What I would like to say that they would not know how to measure the angle in terms of degrees and radians the way we do now. So everything has to be argued in a very different way. The Epicurean philosophers thought that the last piece of geometrical information was evident even to an ass, since if straw is placed at one extremity of the sides, an ass in quest of the provender will make his way along one side and not by the way of two others. Euclid did not care how obvious it was. If some proposition looked obvious, Euclid did not care. To him, many things needed an answering. He arranged and exemplified a toolbox of basic techniques and results that he had inherited. Ways of arguing, ways of proving facts that geometers commonly assumed or used seldom was proved in full. Many things they were assumed. Okay, it will happen like this by looking at the thing and building on your intuition. But what Euclid did was to give them a completely a proper, solid, logical proof. So there cannot be a mistake if you are looking at them in the Euclidean world. Okay. He arranged and exemplified a toolbox of basic techniques and results that he had inherited, ways of arguing, ways of proving the facts that geometers commonly used or used but seldom proved in full. So, this is a very important point. At the end of the first book, he placed Pythagoras' theorem: draw a triangle with one of its sides as a right angle. So, right angle they knew how does the right angle look? Using its shortest side as a base, drew a square whose side is of the same length as the side of the triangle. Repeat the procedure with triangles two longer side, and that you end up with three squares of different sizes resting flush against the three sides of the triangle. Now it turns out that the areas of the two small squares will add up to the one of the largest one that was on the hypotenuse. So now it turns out that the areas of the two smaller square will add up to that the larger one. A startling fact not evident to any ass, which Euclid proved in his characteristically meticulous manner. And so the ideas and the diagrams became harder and more complicated throughout the book. They were purely geometrical sections, a description of how to draw a regular pentagon or hexagon inside a given circle. For example, parts of the book dealt not with geometry but numbers and ratios, ranging from the most basic fact: if the odd number is multiplied by an odd number, then the product must be odd, to a procedure of finding the mysterious perfect numbers who are equal to the sum of their divisors. Finally, Euclid turned to three-dimensional shapes. in the last 11, 12, and 13 books. The last three books of the elements, 11, 12, and 13, were concerned with spheres, with cones, the cylinders, cubes, and cuboids with the regular polyhedra. These were beautiful solids, so there are five platonic solids. And he proved that there can be only such five, there cannot be anything more. But there's a little crux which he tacitly assumed, but he didn't mention. Nothing was known at that time of this concept, the concept of convexity. If you look at the drawings of the five platonic solids, and if you look at them very carefully, you'll always see that those five platonic solids are in the shape of a convex set. Those who know what is a convex set, that take any 2 points, join them by a line, any 2 points in the set, the whole line will lie in the set. If you take any of these solids to be non-Euclidean, non-convex, then this five platonic solids is not true. There can be many such platonic solids. So convexity is a key idea which is subtly assumed, even though the idea has not been clearly spelled out. So this is quite intriguing actually, that so there are little loops and holes in every mathematical work which gradually gets cleaned up as time passes by other mathematicians, and that is the nature of doing mathematics or mathematical science as a whole. So there were just five regular polyhedrons: the tetrahedron, four triangular faces, the cube and the octahedron. The cube, the octahedron has 8 triangles. The dodecahedron has 12 pentagons as its sides, they are all equal. The icosahedron has 20 triangles. He showed how to make such shapes starting from, say, a given triangle or a given circle. He showed how to find their surface areas and their volumes. Euclid's exploration in these final books were frequently ingenious and sometimes applied at almost unbelievable amount of lateral thinking. Despite its gentle beginning and its incorporation of a lot that anyone could understand, the elements as a whole was a virtuoso performance, a road that only the keenest of geometrical minds could follow all the way. It added up to more than 20,000 lines of text in Greek. Euclid was careful, but he was no superman, and both joints and slips were sometimes visible. A few definitions, oblong, rhombus, rhomboid, seem to have been carried across from older sources but never actually used. Quite a number of terms that were used were conversely not defined earlier on. Some words were ambiguous. A surprising amount was taken for granted about the properties of points and lines that Euclid never explicitly set out in his assumptions. So while doing his theorems, he would do a lot of things which he has not stated before. And Hilbert started to correct all this, and there's a Hilbertian system of axioms, David Hilbert system of axioms for Euclidean geometry. So people thought them even about them in the early 20th century. Some propositions were merely special cases of others. Some propositions were strictly speaking unnecessary because they were mere logical consequences of others. But despite such wrinkles, the element was a fine, even an awe-inspiring moment to all that has been done in Greek geometry so far. So some 350 geometrical propositions in the driest of styles. This was the elements, or 400 maybe. It's an odd thing to have one of the most enduring cultural artifacts of the Greek world. This became a real cultural artifact, a symbolism of the Greek world, a Greek science rather. Ptolemaic Alexandria is largely dust today. From wrecked statues are few wrecked statues are dug from the ground or pulled from the sea from time to time. But the splendor is all gone. Ptolemy's dynasty died with Cleopatra. The library is scattered, but the books, the elements among them, the books lived on. So I hope this was a happy starting. And some of the books we will discuss. One book I wanted to show you is the book called Lessons in Geometry, number 1 Plane Geometry. I do not know whether there is number 2 Solid Geometry by Jacques Hadamard, one of the greatest 20th century mathematicians of France. So he was once given the job of actually teaching people who would like to become high school teachers. And what a fantastic book that came out. And you can see it was published by American Mathematical Society. So he is teaching Euclid in a very modern way to the people, to these people who would like to become teachers. If you think that this will be just copy of elements, no, it's not a copy of elements. Many things that you are taught in your school geometry is not exactly taken from the elements. But learning the elements is a different kind of fun. We will also look at the famous book, which is Felix Klein's Vision of Geometry, the great German mathematician near just before the end of the 19th century and early 20th century in Göttingen, one of the great cathedrals of mathematics. So Felix Klein, elementary mathematics from a higher standpoint. So here it's the more transformation standpoint. Rather, in a modern language, the more group theoretic standpoint was first had its root in this book. So we will have some topics to discuss from this book, which is nice, right? Now, the interaction between algebra and geometry, between groups and geometry, with symmetry as the key theme, is a part of this book by A.B. Sosinski. Right? So we will have a look at this book, and if you want to have something of a lot of fun, this is a very prolific author. These are high school teachers. Alfred S. Postminister. No, Roosevelt High School in New York City. He had taught, and also he has taught in the City University of New York. So this book is fun, filled with fun stuff. Lot of things to know about the circle. So there will be many books that will come along, and we will have fun as we go along. So with this, and which is quite a long program, I end and hoping that you have enjoyed it, hoping that you have gained some of the adventures which Euclidean geometry has put forth, the way it has changed the way we think about mathematics forever. So with all kudos to Euclid, whether he was a single person or more than one, we end this program today, and let's continue our journey into this amazing world of geometry. Thank you. Thank you so much.